Hello, this is Mr. Porter. We're going to begin our series today with Pascal's triangle. We're going to try the technology on Wacom today to see how the process works in terms of usability and portability. Pascal's triangle is a collection of numbers. It's a number series and number sequence that has a lot of applications. And so today we're going to focus on how do we actually generate Pascal's triangle. And I'll take it down to maybe 4 or 5 rows and give you some other features and characteristics that students find very attractive and very useful. Here we go. So Pascal's triangle begins with the number 1. Begins with the number 1. And then it proceeds with following ones on either side. Every subsequent row of Pascal triangle begins with a 1. You then find the intermediate numbers by adding the 2 numbers that preceded it. So 1 plus 1 is 2. And you write that sum underneath the 2 numbers that produced it. And then every row in Pascal's triangle ends with a 2. Proceeding, we have beginning with a 1, and then we have 1 plus 2 gives us 3. Again, I'm writing the answer here underneath the 2 numbers that produce that sum. And then 2 plus 1 is 3. And I end that row with another 1. The next row begins with a 1. 1 plus 3 gives us 4. 3 plus 3 gives us 6. 3 plus 1 gives us 4. And then we end that row with a 1. Finally, I'll end with a 1 here for the next row. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. And we'll end with that row with a 1. Now, there are a couple of sequences here, a couple of ideas that I want to stress as it relates to Pascal's triangle. Again, it's a number sequence that can be generated infinitely. There is no end to Pascal's triangle. Now that we've discussed how to generate each row, you can take it as far as you'd like. There are a couple of other ideas that I'd like to present today, focusing on 2 or 3 vocabulary words, one being the row number, the second being the position number. Now, the row number is going to be identified by the second number in each row. So let's start here on row 2, because it's very easy to see that there are 3 numbers in row 2. 1, 2, and 3. The second number, though, is the number 2. That tells us that this is row 2. The second number here is row 3. The second number in this row is row 4, or is a 4, which identifies that this is row 4. The second number in this row is a 5, so that tells us that this is row 5, and it proceeds from there. Going back to the beginning rows, the second number in this row is a 1, so this is row 1. There is no second number here, so this is row 0 to identify that there is no second number. Now that we have the row identifiers in place, let's discuss the position numbers. Everything in every sequence in our counting process in Pascal's triangle begins with a 0, i.e. row 0, row 1, row 2, row 3, row 4, row 5. Begins the same idea with the position locations. In any row, we begin with position 0, then position 1, then position 2, and then position 3. So if I wanted to look at this number here, which is a 6, that would be row 4, position 2, position 0, position 1, position 2. There's a very interesting way that we identify or refer to the addressing in Pascal's triangle, and it is with the letter C. In terms of probability, that would identify a combination. The contrast to a combination is a permutation, and it begins with the letter P. But we're going to focus on combinations as we address Pascal's triangle today. The row number is your first number. Your position number is the second number. So if I wanted to identify row 3, position 3, I would go to row 3 and then count position 0, position 1, position 2, and position 3. That value is whatever the numerical value is in that position. So in this case, 3C3, its value is the number 1. Let's try another addressing mechanism. Let's say I work with 5C2. 2. That means I'm going to go to the 5th row, the 2nd position in that row, and I'm going to get its numerical value. Row 5 is identified again by the 2nd number in the row. So this is row 5. And we're going to count to position 2. So position 0, position 1, position 2. So 5C2 is equal to or has the numerical value of 10. Now, there's another aspect of Pascal's triangle that is also very interesting. Sometimes students may not want to go through the addition process to produce each of these numbers. And there's another approach that we can use to begin that process. I'm going to clear the board now, and we'll look at what that looks like. Oops. All right, so we recall that we had the addressing mechanism of 5C2, and we knew that to be 10 based upon the actual Pascal's triangle that we created on the previous tablet screen here. Now, the way that we can calculate this number, this numerical value 10, is as follows. We first produce a fraction bar. And the number that isn't behind the 2, its position number, identifies how many slots we need to create, both in the denominator and in the numerator. In the numerator, we're going to start with the row number for the first slot, which is a 5. And we're going to decrease that by 1 to get to the number 4. That allows us to fill in these slots. If there were more slots, we just decrease down by 1 until we filled in all the slots. In the bottom, in the denominator, we're going to start with the position number in the first slot. And in like manner, we're going to reduce that by 1 until we fill in all the slots. And then we're going to multiply. My dot represents multiplication and not a decimal point. So let's multiply that. 5 times 4 gives us 20. There's my fraction bar. And then 2 times 1 gives me 2. When I simplify and reduce this fraction, 20 divided by 2 is 10, which exactly matches the value that we found in Pascal's triangle when we produced the entire triangle down to the 5th row. This approach here that we have on this screen does not require that we produce the entire triangle to get to a particular address location. It just requires that we understand what the mathematics is. So today what we've talked about is Pascal's triangle in very simple terms, in terms of how to produce it arithmetically from a traditional standpoint, as well as how to produce the individual numerical values specifically without having to go through the entire Pascal's triangle to get to a particular row or position that we'd like. For example, if we needed to produce Pascal's triangle and I was looking for the 20th row, the 18th position, in terms of land space or paper space that it would take to produce Pascal's triangle to that depth, it would be a very hard task, whereas we can use the process that we used just now with the slots and the fractions to produce the exact same numerical value. Thank you for your time and have fun with Pascal's triangle.